Hey guys, and welcome to today's MCAT question of the day. As always, we'll be working through one of the many MCAT practice problems found at MCATselfprep.com, the home of the free MCAT prep course. I'm Dalton, a 100th percentile MCAT tutor, and today I'll be working through this problem with you as if you were one of my private tutoring students. Today's practice problem comes from the end of lesson mastery quiz in lesson 6 of the Biochemistry 2 module. Be sure to hit pause and try this problem for yourself before watching my explanation. All right, so in order to ace this problem, we need to have a basic understanding of the layout of a cell membrane, as well as some important intermolecular forces that come into play a lot of the time in our body. So the cell membrane, as you might remember from some of your classes, is basically made up of these different molecules that have a head and then these two fatty acid tails. They have these two chains, and these chains are made up of carbons and hydrogens. Now this part outside the head is hydrophilic. It really likes water. Whereas these tails, since they're these long carbon, hydrogen fatty acids, they don't like to interact with water. They're hydrophobic, and so they'll come into the inside. The heads will want to go on the outside, and the tails, the fatty acid tails, will want to go on the inside. And so we'll get a layout like this, where we have all these fatty acid tails inside the membrane together. Now, it's important to recognize that these fatty acid tails are made up of carbons and hydrogens. We've just got a lot of carbons bonded to a lot of hydrogens. And because that's what we're dealing with here, we're going to deal with something called London dispersion forces. London dispersion forces is one of the weakest type of intermolecular interactions that we'll have. See this London dispersion force here, and it's this slight interaction that makes these want to stick together. Now, there's other intermolecular interactions that are much, much stronger. For instance, hydrogen bonds are much, much stronger. But hydrogen bonds occur because we have this unequal distribution of charge. So imagine you have a water molecule like this, okay? And we know that the oxygen is much more electronegative than these hydrogens. It's gonna want that electron density, that negative charge, much more. So it actually pulls some of that electron density towards itself, which leaves it with a partially negative charge. Even though the molecule as a whole is neutral, you have a partial negative charge on that end, and a partial positive charge on that end, on this end. So we know that opposites attract, right? So if we have another molecule, like let's say it's another water molecule doing the same thing, well, the partial positive here will get it attracted to the partial negative on this oxygen, and that creates a hydrogen bond, which is another type of intermolecular force and is even stronger than London dispersion forces. Now that we have that understanding, let's go ahead and take a look back to this question and see what we can figure out. All right, so looking at this question, we have a cell biologist who's comparing membrane extracts from two different cells, a liver cell and a skin cell. And the key here is he notices that the fatty acid tails in the skin cell's phospholipid bilayer are 1 nanometer longer. So remember, we were looking at that image earlier of the cell membrane. These tails are longer in the skin cell. We've got longer tails. That's what he's noticing. And we want to know which cell will have the greater melting point. Let's start with this answer option right here. The liver cell will have the greater melting point because its fatty acids experience greater London dispersion forces. Notice this. We're tying the greater melting point to greater intermolecular forces. And that's key because think about it. When we're melting something, we're taking it from being a solid where things are locked into place pretty good and stay where they are, to all of a sudden we're changing it into a liquid and things aren't connected as well. They start to slide past each other. They're able to move more. And so it makes sense that if something has stronger intermolecular forces that are sticking those molecules together, making them not want to move as much, it's going to take more heat to melt it. So greater intermolecular forces equals greater melting point. So that part checks out. But do we really think that the liver cell is going to have greater London dispersion forces, greater intermolecular interactions? Well, look, the skin cell is longer. And so there's more atoms in that molecule. There's more carbons and hydrogens. So there's more opportunity for interaction and stronger force than there is in the liver cell. It's like, imagine if I got my hands sticky and they all of a sudden wanted to stick to each other, if I had longer fingers, there's more stickiness happening. It's going to take more strength to pull that apart because there's more surface area for that to stick to. It's the same thing here. So the skin cell is actually going to have greater intermolecular forces. This is going to be incorrect. Now this one, if we go down here, the skin cell, okay, that checks out, the skin cell. because it experiences more hydrogen bonding. Now that sounds right, but remember, hydrogen bonds come when we have these partial negative and partial positive charges. That doesn't happen with carbons and hydrogens. You usually see hydrogen bonding if there's a hydrogen bound to an oxygen or a hydrogen bond to a nitrogen, because the electronegativity difference between hydrogen and an oxygen or nitrogen is so different that you get that partial negative, partial positive. The carbon doesn't really want electron density much more than a hydrogen, so you don't really get those poles, and so you don't see hydrogen bonding. So this is going to be incorrect. The liver cell here experiencing more hydrogen bonding, that's going to be incorrect for the same reasons we talked about above, which means that leaves us with this option. The skin cell will have the greater melting point because it experiences greater London dispersion forces, like we talked about. Let's check it out. Awesome, perfect. If you enjoyed this MCAT question of the day, be sure to give it a like. For more MCAT questions of the day, be sure to subscribe to this channel and enroll in our free MCAT prep course found at mcatselfprep.com. Now, if you're really looking to maximize your MCAT score, be sure to check out our elite tutoring services and request a free consultation with any of our available tutors. We'd love to chat with you about your situation and how we can help you maximize your MCAT score. We look forward to hearing from you, and we'll see you next time. Have a good one.